In this presentation, we're going to extend what we talked about in the previous presentation where we found derivatives of the 6 inverse trig functions. Now we're going to focus on the antiderivatives of the inverse trig functions. Now remember, the two most important ones were the inverse sine and the inverse cosine. Let me remind you of those two derivatives right now. All right, let's try some examples. All right, so let's say we have the expression 6 over square root of 1 minus x squared, okay? So the 6 is a constant, and we can set that aside. And we see right away we're looking at the result, right? The integrand is the derivative of the inverse sine function, okay? Remember, never lose sight of this, everybody, right? This right here, that's the derivative of some function. We'll call that function capital F. That's the derivative of it. What's the original function? In this case, is the inverse sine. Okay, what about this? Well, notice, gang, the integrand is consolidated. So what I'm going to consolidate in the sense that it's simplified, where the dx appears in the numerator instead of off to the side connected by multiplication. So I can write like this. We don't lose anything. I'm just going to move it over. Okay. So we look at that integrand now, that fraction 1 over 1 plus 16x squared, and it suggests the inverse tangent function. But that 16, right? What about that 16? So here's what we'll do. I'm going to use a property of exponents, and I'm going to rewrite 16x squared. Okay, 16x squared is the equivalent of the quantity of 4x raised to the second power. All right, now if I scroll back up, notice that's starting to shape up looking like this right here. Okay, in the denominator, I have 1 plus some function squared. Okay, 1 plus some function squared. So in our example, we have 1 plus some function, in this case, is 4x. Notice also, kids, notice also, in the numerator, we need the derivative of that function. What is the derivative of 4x? Yeah, good, it's 4. Do we have that in the numerator? No, currently we have the number 1 in the numerator, right? We don't have a 4, but that's okay, we can fix that. We can always fix constants, can't we? Let's multiply by 4 on the inside. Divide by 4 on the outside to compensate. Okay. Now we say the integrand is a perfect inverse tangent. The derivative of, excuse me. I'm getting carried away. All right, but otherwise I'll set that 1/4 aside, and this is going to give us the inverse tangent of 4x plus a vertical shift. Okay, how about this one? What do you think? Do you suspect a chain rule? Yeah, it sure looks like it, right? The derivative of the cosine function is minus the sine function, right? Now you've got that in the numerator. So I'm going to let u equal the cosine of x. Then du is equal to minus the sine of x dx. And I have all of that in the numerator except the minus sign. So let's fix that. Let's multiply by a -1 on the inside and a -1 on the outside. Let's see what this gets us. Okay, and then we get 1 over the square root of 1 plus u squared. Now what? Our inverse sine and inverse cosine functions have the square root in the denominator, but they've got 1 minus, not 1 plus, don't they? Right. What about, is it inverse secant, inverse cosecant? Well, there's no expression that goes in front of the square root symbol here. So it looks like we're at an impasse. Looks like we're going to have to try something else. What could that something else be? So if we start back at the beginning, what could we do? What do you think we could do? Any ideas? Yeah, we may very well need some kind of a technique. You're right. We may need some kind of a technique because our substitution didn't lead to any one of the, or at least didn't look like any one of the 6 derivative of the, the 6 inverse trig functions that we discussed in the previous presentation. Once we got to this step right here, right, that's not right, it doesn't recognize, I don't think any of us recognize what that's going to be, 1 over the square root of 1 plus u squared, because at that point, there's no chain rule anymore. All right, so in that regard, we're going to need something else, okay? And luckily, not in this particular presentation, but soon there's an entire chapter devoted to solving these kinds of problems. It's called techniques of integration, all right? Techniques of integration.